So we'll do the first example here, which is an explosion of stuff. I just put a balloon blowing apart. It doesn't really work this way, but I thought it'd be less violent than something else that could explode. So we'll look at this, and then we're going to go into a completely inelastic collision, which is the next level of difficulty, and then we're going to finish with an inelastic collision, which is the hardest one. So each one is going to add just more work to it, but the process will be the same from start to finish for each of them. So you can read this question here. We have an inflated balloon that blows apart into 3 pieces, and we want to find the velocity of the third part after the explosion. So this is also kind of new to us because we haven't worked with 3 objects yet. We've only dealt with 2. So we're just doing 3 just because, and we're going to work through this together. Okay? So take a moment, read the question, draw your system diagram, and I'm going to draw mine, and hopefully ours will look the same. And while I do that, I'm going to do the attendance.
Oh, that makes sense. Okay.
Okay, time's up. So we have 3 pieces, right, blowing apart into different directions. We have a piece going southeast, we have a piece going north. Yep, and so we have a third piece. Which direction did you guess the third piece is going? What's your intuition tell you? Yeah?
Southwest.
Southwest? Sure. Yep, I would guess west for sure because initially remember there's no momentum before the balloon explodes. Right? So after the explosion, if there's an east momentum, there has to be a west momentum to cancel it out. So we can guess that the piece is, something's going to be going westward. And then the north-south, it's anybody's guess which direction it's going. But if you look at the answer, you can see that it is southwest. So we can check that there too. Okay, so if we draw our diagram here, right, I'm going to draw just like a pie, split into 3 pieces. So this is piece 1, piece 2, and piece 3. So they're stuck together. There's nothing very exciting about the initial diagram. The second diagram is going to start in the middle again. I have piece 1 going out this way, so I have P1 F going up that way. Right? I have the second one going south 10 degrees east. So it's going to go like this. And if I do my components in here, it's 10 degrees. So this is going to be V2F, V2FY, V2FX. So I'm guessing my third piece is going somewhere over here. Again, because I need something going west to balance out my east. And I have a line going north. I don't know how much I have going south yet, so I guess going south. If you guess north, so be it. There's no problem with that. You're not going to get the wrong answer. V3F, V3FX, V3FY. And then we have an angle in there. My diagram makes sense to everybody. So I phrase this question so we can get rid of a lot of variables, but because we have 3 different objects, we have 10 variables. Right? We have 11 variables. We have the mass of each of the 3 objects, and then each object has more than 15 variables. All right? Yeah. Each variable has, each object has a speed initially in the x direction, a speed final in the x direction, right? And so if we go through each thing, each object has 5 variables each times 3. So this is where by 11 it's 0, but I'm just going to go through the whole process with you, just so you can see it in its full extent. So if I do mass 1 is 10 grams. Mass 2 is 0.2, 1 grams. What's mass 3 that's out there?
0.020?
Yep, so also 20 grams. Perfect. And then since we have 3 objects, I'm going to write them all out. Talk about subscripts. We have 3 subscripts here. We have the object, which is the number 1. We have the x component, which is why the x is there. And then we have the I for initial. So we have 3 subscripts for each variable. Okay? So, 0, oh, and I didn't say what's positive. So I'll say cells positive and piece positive. So, yeah.
Would you want to write V instead of M because it's the velocity?
Oh, I do. Well, I'll take that anyway. A little bit already. Start. Only have eyes in the back of my head. Okay, so we have velocities. We have, that's half of the battle there. Right? And now we have to do a chart for the y direction too. So again, just like energy, I'm showing you a process that's going to solve every problem. You can see there's corners we can cut here, right? We don't write down all the zeros, we don't want to. It does save you time, but it doesn't help learning the process. Right? If we go through the y, right, we'll go through the y part too, kind of picking things out as we go. We have V1, yi, 0, V1, yf is 10, negative 10. V2, yi, 0, V2, yf is 5 meters per second. Alright, so we have a large table here. Is everybody understanding what's happening so far? So whether you make one big column on your page or do two columns for the X and the Y like we did before, that's personal preference and there's no wrong way to do it. So we haven't obviously started to answer the question yet, we just have a table of values. Alright. So our next stage is pick a direction and work with that. So which direction should we work with here?
X.
What would you choose? Brandon, what do you choose?
X direction.
Sure. There's no wrong answers. What do you want to do? X direction it is. Any reason why you chose the X direction?
Not really. I guess the X direction for the first piece is 0.
Yeah.
It's a little bit easier. I don't have to worry about that one.
Yeah, perfect. Right, let's work in the X direction. So we start with the law we're using, right? The conservation of momentum in the X direction. Right? Then just going through the steps, right? General process. We're going to write a line that has the momentum for each object before and after. So there's 6 that go across here. So here we go. M1 V1 xi plus M2 V2 x plus M3 V3 xi xf M2 V2 xf. Alright, so good, my equal signs line up. Right, but that's our general second statement, right? You have the momenta for everything included there. And then after this is when we start to simplify and make our life easy. 4 of those things don't belong there, right? What are the 4 things that don't belong? What do we think here?
The entire left side and
Yeah.
V1 and 1.
Yeah, good. So wherever we have zeros for velocity, right? So this disappears, this disappears, this disappears, and this disappears. All right, so all of that disappears. So it goes for something that's a little overwhelming to something very simple, right? To get V3 xf, we go trying to find negative M2 V2 V xf or M3. Right, so if we rearrange it, I skip, maybe some of the rearranging steps. But there's where we get to. Is there anything else we can make our life easy? Or should we just plug in the numbers and figure it out? 100?
Why are you doing velocity on the other side?
That's not fine.
On my velocity?
Yeah.
Oh, okay, what about X?
We're good.
Oh, never mind. Yeah, that's the axis.
Yeah. Yeah, these are all subscripts, right? These aren't like a multiplication of something.
You know, I thought of it as the X plus the X part in the strings.
Right. No, I totally get it. Because it's not on a blackboard, so you differentiate between subscript and like upper lowercase.
Yeah, when I see it,
Yeah.
sounds stupid.
Yeah. What else can I get rid of? Anybody else see it? There's something else that just would make our life easier. Well,
M2 and M3 are value.
yeah, M2 and M3 are the same value, right? If we look at our table of values. So we can actually cancel those out too now. And there's no math involved here, right? Just negative 5 meters per second, sine of 10, whatever that is. Like I said, rules of math. Right, so that's going to work out to be a number. What, I don't know what that number is. Along with that.
Negative 0.87.
Alright, that's good. We knew it was going to be going west. So it should be going negative east, so we're good. Check. Okay, and then lastly, not lastly, we have to repeat the whole process again for the y direction, right? So let's see if we can race to get it done first. Me and chalk or you on paper. Alright, so again, you start off with the law that you're using, which is the conservation of energy here. So we'll go through all the steps. Alright, so again, we write it all apart. So the order of the subscripts doesn't really matter. So yours are different than mine, okay? Again, the left side all cancels out, so but not any, everything on the right side still remains. So that makes it a little bit different than it was before. We can roll 0 again. Again, now, right, when we rearrange the equations, we're taking the momenta of 1 and 2 to the other side. But there's no canceling of masses this time because they're not all the same. Right? Mass 1 is different, so you can't, it's not a common factor anymore like it was before. So just be careful when you do all this, right? It is a lot of note-taking stuff, but you gotta take your time to make sure everything goes in the right spots. Right, so we rearrange it, we throw all our numbers into the equation. Again, taking our time to remember there are negative signs there, so we got to be conscious of that as we go, that we're not canceling things out as we go. What does that line work out to be? I guess it's a really small number. Going to good.
0.076.
Sounds good. Okay. We're almost at the end. We're done 2/3. We only have a third of the way to go. Then, what's the next stage to find B3F? What do we do? Well, yeah, use the Pythagorean theorem, right? We have both the x and the y components. I'm just going to erase the table values here. So if I use the same triangle I had before, you can also redraw it if you like, right? So we have our B3F is B3Fx plus B3Fy squared. So I'm going to guess that. I don't know what the actual, like, more than one decimal number is, but that's close to what it was. You can double check. And then the tangent ratio to end this. Offset over adjacent. Right, so using the triangle that I drew in yellow, right, my offset over adjacent is y over x, which is different than how I got the answer up here, which is x over y, which is the same spot. Yeah.
I didn't get this for velocity. I got like 9 point something.
It's because you didn't keep the negative, because one of them is negative.
Because if you do like the opposite of tan of this, it's not 5 degrees, it's 0.087.
Where's that?
Like over here.
Here?
Yeah.
Sorry, what do you have?
Oh, never mind, wait.
The calculation thing first.
Oh, never mind.
Yep. Probably the longest question we do all year, something like that. So your therefore statement at the end would be, therefore the third piece of the balloon travels, or has a velocity of 0.87 meters per second at in direction of, in my case, west, 5 degrees to the south. Anybody have any questions? The next question is not this long. The last minute. We're all okay? Okay. The next one then, take a look at it together here. Again, read the story, draw a picture. Don't write it down, it's a long story. I'll talk about what we think the answer should be before we actually do the math. Okay, so we digest the problem. If you had to guess who's speeding, if there is somebody who's speeding, who would you think it is? Is it Jackson or Nan? Based on the stats you're giving up there. Not based on personalities or stereotypes. Jake?
Probably Jackson.
Why's that?
Because he's in a car which has a lot less mass, but somehow it cancels out and gets to almost 45.
Okay. Yeah. What do you mean by cancel out?
Like, if they were both going at the speed limit,
Mhm.
it would go like further towards the east.
This might further towards the east.
Oh wait, no, I got them. They were going to be other ways.
Okay. You want to change your answer?
Yeah, but
Pardon? Well, they can't cancel it if they're not directly, if they're not at each other. Canceling out would mean one's going south, one's going north. So So who would you guess is speeding? Well,
Jackson, because at the end they're going more east, and he's in a car traveling east.
yep, I go with that. If you look at Jackson's car, take what Jake said and slow combined together. Jackson's car has less mass in it, right? When you compare it to the truck. But at the end, the wreckage is going more east than north. So that tells me that whatever was going east had more momentum before the collision because the wreckage is going more east after the collision. And since Jackson's car was less mass, he had to be going a lot faster to have more momentum than the truck. I'm just guessing, but that's kind of what I'm guessing. You guys follow my logic? Right? So you gotta know how everything kind of related here. So let's go through this mathematically and figure it out. So we have an intersection. Here's my intersection. We have Jackson's car. I'll put Steve's car. And in her truck, put Steve's truck. My velocity initial of the car in the x direction going that way, and the velocity of the truck. Velocity initial of the truck in the y direction. All right, so you have your truck and your car coming together at the intersection, and they're going to collide. Afterwards, obviously, if you're going, I find it distracting. So I'm trying to figure out what's more important than what I'm doing right now. You know, flip your flow over and just like put it away. Okay. Afterwards, they combine together. They move off in a direction like this. Car, truck. And our velocity of the car is equal to the velocity of the truck, right? Because it's a completely inelastic collision. All right, we're good. Yeah, Hunter.
So, just out of curiosity, what changes the problem? It's just like perfect and elastic. And the other one.
What do you mean?
Like, does it change anything in the problem depending on what it is now?
Yeah, it does kind of because it's completely inelastic like this one here, right? Their final velocities are the same, so when we do our big equation, we do some common factoring.
Okay. And what if it's not? That would change it to like you cross it out and it's not 0.
If it's in a straight line, yeah.
All right.
That's kind of the next question, I think.
Okay.
Yeah. Okay. So if we go through this, right? I'm just going to table values underneath. I have the mass of the truck is 2,275 kilograms. The mass of the car is 1525 kilograms. We only have 10 things in our table values this time, not 15 like we did before. I probably shouldn't have started so low. So we'll go back up to the top. The velocity initial in the x direction of the truck, which is 0, right? The velocity initial in the x direction of the car, which was something we don't know. So I think kilometers per hour, and we go east. We have the velocity in the y direction, or final in the x direction of the truck, which is equal to the velocity final in the x direction of the car, which is equal to whatever it was, 31 kilometers an hour. And the angle, I do this not very well. Yeah.
Mr. Eckl, I think that angle is 43 degrees.
Pardon?
I think the angle is 43 degrees.
Oh, it is 43 degrees. Yeah, thank you. Right, so we have those components there. All right, so obviously not as robust as the last table values because some of the things factor out. Okay. Then we have the y direction, same thing. We have the velocity in the initial y direction of the truck, which is what we don't know. The velocity initial in the y direction of the car, we do know is 0 meters per second or kilometers per hour. And velocity final in the y direction of the car is equal to the velocity of the final in the y direction of the truck is 31 kilometers per hour sine. Everybody with me? Okay. So, and like we did before, right, we're going to go in the x and the y direction. So which one should we do first? Maddie, which one would you like to do first? X? Sure. One thing about momentum, too, is that we don't have to convert to meters per second. You can leave it in kilometers per hour, because in the end, we're just dealing with ratios. So you can convert to meters per second, and you get the same answer as if you keep it in kilometers per hour. So I'm going to be lazy and keep it in kilometers per hour. So that way, whatever answer we get, we can directly compare to 35. All right, so we set the x direction. So here we go. Right, we have px. I equals pxf. We have m1b or b mt b c x5 plus bc x5. Right, so we have our standard two lines, right, when we put them together. How can we simplify this for the next line? There's two things that we can do mathematically. What disappears? Sloan?
The initial speed of the truck in the x direction is 0.
Yeah, so the velocity in the x direction of the truck disappears. Right, that didn't have any. And the other thing we can do is to what? Under?
Can you factor dt on the right side out and take it as t plus mc?
Yep. So we can factor out the velocities on the other side. Not something you have to do because we know what they are. So if you rather just put the numbers and figure it out, you can do that too. Right. So we're trying to find v, c, CXI, right? And if we do 100 then we can factor you guys out. I'm going to change it to VXF, they both have the same. Oh, by the way, M, C. So we got. So make sure you, again, take your time, work your way through it. Make sure your masses go in the right spot. Sometimes students go too fast, put the wrong masses in the wrong spot. Right, you sign both sides of the line. And the end, want their speed here. Alec, what do you get?
I got the speed for the car as 64 kilometers per hour and the speed for the truck as roughly like 40 kilometers per hour.
Okay. And what do you get?
I got 56.494.
Yeah, that's right. Yeah. Anyone else get 56? Yeah. I don't know what you did wrong, you know. 56 point.
494.
So Jackson, speed. Okay. You go back, I would like you on your own to do Ant's truck and see what you get for that. I think it's around 35. Pretty close to it. I'll figure it out. What's you wrong?
I was multiplying by 35 and 31.
There you go. I think Ann is like 35.3. Here's the third problem. Once you get that one, if you need help getting 35, let me know. This third one I'm going to leave to you guys. And